My name is Cynthia Liem, and I'm an assistant professor at the Multimedia Computing Group of the Faculty of Electrical Engineering, Mathematics and Computer Science of Delft University of Technology. What I work on is on artificial intelligence techniques that basically make humans broaden their perspectives. I think that discovering something new really is the essence of, well, life, science, teaching, but also scientific inquiry. There's a lot of data these days that we can learn a lot about. There are many large collections to oversee and to explore. We as humans may kind of know what we want to get out of them, but at the same time, not really. And I'm really looking for techniques that help us to oversee these large collections, the large sources of data we have these days. I want to make use of human perspectives in there who indicate that something is better for them or more interesting. At the same time, look at data traces, at the description of content, at the way people interact with the content. But I'm particularly interested in that we actually don't know yet, which means that there is no data yet on that humans don't know yet what they think about that. And still, I do think that with the help of technology, we can still make something out of it. We can still confront people with that, and thus lead to filtering techniques that are trustworthy, that help us to really broaden our horizons.
My name is Annibale, and I'm also from computer science at TU Delft, and I mostly work in software engineering. And what we do in software engineering is to establish the best practices for developer to follow to build a software that is actually working as intended, is trustable, and is free of faults. At least we try to guarantee there's as fewer faults as possible. What really fascinated me actually is not to do testing in a manual sense, but use automated techniques. So how we can automate the process of verifying and validating the software itself. And this means that sometimes we have to combine multiple techniques, sometimes even machine learning itself, to help to find bugs, also sometimes in machine learning itself. The very fascinating thing is when that the technique we have to use, they need to change depending on which type of software we are working on. For example, if you work, for example, in machine learning, then we use some category of, we have to combine a certain category of techniques. If you look for fintech software, then we have to use other techniques. So the really things I like the most is that how we combine and which technique we have to choose strongly depends on the problem itself. So there's a lot of study, a lot of understanding of the peculiarity, and only then when we understand what's the properties of the software, we can think the best strategy to do that. It's a bit of work, but the fascinating thing is once you have done this, you know exactly how to do automated process. So you do one click and you have, for example, report for you to tell you what are the most critical part of the software. The AI, so artificial intelligence nowadays, is a hot topic. You can see these keywords in the newspaper, blog posts. Everyone is talking about it. And also this happens in the software company that sometimes now they try to, for example, replace part of the system that would ask people to write with machine learning. If you think about self-driving cars or object detection, manually writing all the rules that define an object is not that simple, and maybe it's not even a clear definition for that. So we usually tend to rely on machine learning that extract the patterns for image or from other type of data. So it's getting very popular, and which means that there's a huge trend. So if you see many companies, we have many of the advertisements out there, we have outstanding new brain or something for a specific task. But then this very fast speed toward machine learning actually is removing or cutting down a lot of checks we would do if we ask the developer to write software. We will write more test cases, we will write robust like performance analysis, we will check for critical system. When it comes to machine learning, we fed up, we put all the data within a model, we get an answer, and if the accuracy is okay, we're happy with that. But what happens to the critical cases? What happens if, for example, in the self-driving cars, we have a road and there are specific situations with more than one pedestrian? It's not just a number, it's a case that is very dangerous. How does the system work for that? So we need AI because it's the future and makes to allow to scale up a lot of difficult tasks. But on the other hand, increases the challenge of understanding what's actually going on in the model.
And I do think that this focus on the corner cases is very important here. There is a lot of societal debate currently too about unethical behavior of AI systems, maybe discrimination or bias or other unwanted inferences that are being made. And what you see a lot out there is that actually what happens is a consequence of a bigger socio-technical system where there are different components that interplay, but we only evaluate a small part, being that AI recognition part. If the data already carries certain biases that come out certain processes, you also want accountability on that. You want to treat it as part of your bigger system, which from a testing perspective would actually be very natural. From a software engineering perspective even, it might relate to requirements. And actually having that one corner case in 1,000 that goes horribly wrong is then as important as doing it right in 999 of the cases. So here again, I do think that the software engineering mindset, the testing mindset is something we should include if we want to become more resilient, if we want to be able to not only look at what goes well, but also at how we can improve on what doesn't go so well yet. Actually, Anibal and I met when we were both teaching on the same course. He was the overviewer of the project course and I was having one of the projects in there. And rather quickly when we spoke about our students' work, he actually indicated to me that it sounded like my interests were quite close to his. Basically, I was trying to figure out then how to recognize books on bookshelves, which means that you have to deal with noisy data, maybe robot vision, different interpretations of what you see in the scene, and probably even a more cyber-physical system that makes decisions based on that, which was actually quite close to what he was interested in.
So this is how we met in terms of academically speaking, and we were start discussing how we can cooperate. The main point we started discussing is how we can apply existing software engineering methods and testing techniques on, for example, bookshelf detection, how we can detect the books. So there exist plenty of practices that developers, human, follows nowadays when they have to write software, and they're well established and many companies use nowadays. But when it comes to machine learning, for example, in the case of bookshelf detection, we replace somehow humans that would write the software with an optimization method that would write the code for us. The problem is that when we work with human, we can tell the human what are the guidelines, the best practices to follow. When it comes to machine learning, it's like a black box. We run it, we give a lot of data, at the end you have an output. We don't really know how we know how the output came up, but we don't know why that's the best output. It's the best in terms of optimization, but what happens to the corner cases? How we have guarantee that actually it's not gonna fail in the future with new data. And the collaboration really has we have two different perspectives, like looking at machine learning as pure optimization, everything is correct, but also from the side of companies that have to deploy machine learning within a context, within a domain, how actually we make this working. And we can think about self-driving cars, right? So we can have object detection. We have plenty of research in machine learning for object detections, but when we deploy it within a car, we are interested in certain type of detection. We don't care if you can distinguish the type of dogs, but we care if you can distinguish a human being from actually a static object.
Yeah, so I was actually saying that I'm quite interested in discovering that what we don't know yet. And this was something I was a bit struggling with, coming more from a machine learning perspective. Because very often we would indeed just define a few objects of interest and then just see how accurate we would be on those. Meaning that you really only look at that what you know and try to optimize for that. But thinking of bookshelf recognition or more elaborate safety critical situations, some errors are worse than others. Some mistakes really cannot be made, whereas others are fine. And that is actually, as Hannibal said, very domain specific and still warrants structured large-scale approaches to automate this. So that's why I do think that our two interests were meeting quite well.
I also want to add a little bit that there's a lot of fascinating joint topics to work on, but this is a bit of the challenge when we have to do interdisciplinary research. There's plenty of terminology that actually we share with the same words, but sometimes with different meanings. We learn a lot from each other to a greater good, I would say, so to improve, for example, the state of the art.
So speaking about these different ways to evaluate, to test these different requirements, here is a concrete example that illustrates that further. Here is a picture of a traffic scene. And from an object recognition, there are many different objects to recognize in there. There is a bus stop, there is a truck, there are lots of buildings, there is snow. What we could do if we really focus on those objects and we want to classify them all, is to train a classifier to show them many examples of trucks, many examples of bus stops, many examples of buildings, and then having these classifiers decide whether they indeed can recognize those all in a picture like this.
All right, but from a software engineering perspective, right, not all objects that we see in the actual image is actually what really matters. It depends on the context and depends on what are the requirements of the system itself. Let me make an example. Assuming we have, for example, working for self-driving cars, and we want to deploy our object recognition inside a car. In that case, for example, we don't really care whether the machine learning is able to detect the label of the brand on the truck, but rather what are the critical elements in the environment. For example, the distance to the truck, or if there is a person that may actually cross the road in any moment. This is what really matters. So, for example, misclassifying a window with the door is not that important. So requirements, the domain is actually the key when we think about the software engineering aspects.
And that makes the evaluation of the output of any recognition based on a scene like this very tricky. This would be the output of a default object classification algorithm that's been trained on indeed a lot of examples. And if we look a bit more closely, we see that the truck is being recognized, all its wheels are also being recognized. Not all the windows, just that one that's in the corner. Many of the buildings though. And the bus stop is being recognized as a land vehicle. That's an error. At the same time, if this were a self-driving car looking at this, if it thinks this is a land vehicle, actually it may behave more carefully because the land vehicle may move and the bus stop may not.
For software engineering perspective, I would say that, for example, here the requirements are half met some way. There is a good detection of the vehicle that appears in the scenes, but the person is not detected, and it is very, very critical. We want that the car does not kill anybody, and so safety here is extremely important. So maybe from an optimization perspective, we could say that most of the objects are somehow recognized, but the one that really matters for the security and for the safety of the people is not met there yet.
So in other words, if we would have a classifier that's 100% correct in all the windows, which this classifier is not, by the way, but if it were, it would be very important if you really want to recognize all the windows, but not in the case that Annibale just discussed, where you have this safety-critical situation. Now here is another example, again of a road scene, and this time it's a scene in the dark, where it's crowded. In this corner, people are at traffic lights, many things to see that are having a lot of light behind them, but they are billboards, advertisements. And if here I would run an object classifier again, this would be the outcome of that. Basically, one person in this case is being seen, which is the person on the billboard. Arguably, that's the person, a very visible one. But probably, again, thinking of a safety situation, none of these people are being seen at all.
Indeed, I can also add that in terms of self-driving cars, here the dangerous situation is that we have many people on the side of on the corner of the street. They may actually cross the road as long as the traffic lights changes. So here is actually the requirements not met at all, because the critical point is not the banners. That person is not going to move, but all the pedestrians are what really matters here. So again, maybe the object recognition is not bad in terms of numbers, but software engineering is very bad, critical situation.
And again, there are also different artifacts out here. So you have your object classifier, that's one piece of software that just outputs labels. But if this were a car, then actually there is also an associated action. So if you see a red traffic light, you want to stop. You don't only want to recognize the traffic light. Yet again, that does mean that as for evaluation and as for testing, we have to be really specific on what we really want to assess.
So we are actually collaborating, and what I really hope for the future, that throughout our collaboration, we can, in one sense, change a little bit the mindset of the fields, because we work in two subdomains, even within the same computer science, so it's the same big field, but there are so many subfields. In our case, there are two very strong subfields with dedicated venues, but also different standards to do evaluation. And we look sometimes at the same problem, or with two different perspectives, but to solve the underneath problem, we need to look at both sides. We cannot say we solve the problem if we just work independently, because we look at two faces of the same medal. We need both of to rebuild the medal disease. So that's really, really important. That's what I wish for the future.
And another thing that I would really like to see in the coming years is for us as scientists to work much more on the actual impact of our work. There is so much talk now about societal impact, practical impact, being useful for society, where it's sometimes a bit hard to concretize that because we have so many things to do. In this case, we work on a project that is academic in nature, that crosses actually two different fields. That is very illogical in some way too. We get much more encouraged to be very strong in our own subdisciplines and get grants on our individual expertise, or find partners outside of our institutes. Whereas it is much harder, we had so far to do it in hobby time, to work together if you're two colleagues with similar interests in even the same faculty. I mean, we worked on that, we're also working on the funding, but as that grows, we will get something better, which goes across domains, which also will be relevant for more people even than scientists alone, which also will be useful, we think, for industry, and even for citizens who might also have a certain take on how things should be assessed or evaluated. So there I see a lot of potential that goes far out of the traditional realm of what an academic is supposed to do, but that I do think now needs a lot of proper formal attention, and we're going to work on that. And I hope many more will follow suit.